very important result, prove that, so this is prove that 4z multiple by 4 over 12z. So this is this. Now this is isomorphic to Z3. This is a module congruence. This is a modulo 3 group of additive integer of modulo 3. So this consisting only 3 elements 0, 1, 2. Now this prove that this is isomorphic to this group. Then additive group of residue classes modulo 3. So this is a additive group of residue class modulo 3. Now this is again very important question. So this is in 2015. So this is in examination 2015. So we will apply fundamental theorem of homomorphism. So in this question we will always apply fundamental theorem of homomorphism. So we take this from mapping from this to this. This is mapping from this to this. Then prove that homomorphism onto. Then this mapping is isomorphic to this by kernel of F. And then prove that it is a kernel of mapping. So simple. Now first check that which kind of these set. So what is 4Z? So it is a subgroup generated by 4. So its elements are multiple of 4. So its element are multiple of 4. So this is a 4 and then so on. So it is a multiple of 4. After that, this Z3. So what is Z3? It is a 0 bar, remainder modulo 3, 1 bar and 2 bar, right? So this is of modulo 3. So this also written as of this as this way. So there are two ways. Some books use this and some book use this. So you can use any of the notation. So this either this notation or this notation. Now it is a additive group. So this is a additive group of residue class, group of residue classes modulo 3, right? So first check that the element of a group. Now define a map. So define a map F, right? So this is from 4Z to Z3, 4Z, so Z3. So when we divide, so this is by F of what is element of 4Z, multiple of 4. So this is a 4n and what is its element? So this is a class of n, this values. So this is a residue class of n for every n belongs to Z. So remember that. Now first to prove homomorphism. So if to prove homomorphism, I take x and y. These are two elements belongs to 4Z. So it means x is equal to 4m and y is equal to 4n and Mn belongs to Z, this values. So what is f of x plus y? So this is f of, because it is in addition, 4 times m plus 4 times n, this values. So what is this? It is f of 4 times m plus n, right? So if m is integer, n is integer, then m plus n is also integer. So remember that. If m is integer, n is integer, so this value is also integer. If this value is also integer, so this total number is divided by 4, या multiple of 4. If total number is multiple of 4 by using this definition, so this can be written as residue class of m plus n. This can be written in this way. Now, this residue class of m plus n can be separate residue class of m plus residue class of n. So what is this? It is a f of 4m plus f of 4n. So this is a f of x plus f of y. So it means f is a homomorphism. So that is my first part. Second, onto. So clearly it is onto. Why? Because for every this residue class belongs to Z, this values Z3. So we have n belongs to Z such that this value f of 4n is equal to residue class of n, right? So it means f is onto. So it is homomorphism and onto. So it satisfies all the property of fundamental theorem of homomorphism. So what we get? We get f mapping from Z4Z, this is 4Z, to Z3. So this map is homomorphism and onto. So by fundamental theorem of homomorphism. So you write the entire statement fundamental theorem of homomorphism. It implies Z3 is isomorphic to 4Z by kernel of F. 4Z by kernel of F. Now to prove that kernel of F is equal to 12Z. So kernel of F is equal to 12Z. So what is kernel of F? So kernel of F. Now here if I take some element, so this is 0 modulo. So what is kernel of F? So this is 4n such that its image is equal to 0, which is this 0 values, 4n of 0 values, right? So this is this values. Now this set is 4n such that what is its image? This is residue class of n, which is equal to residue class of 0, this values. Now it means This means 4n. This n is multiple of 3 such that n is multiple of 3. So every multiple of 3 is the identity element, 0 element. So it is a multiple of 3. If it is multiple of 3, so n can be written as 3k. So n can be written as 3k. If n can be written as 3k, so this term will become 12k such that k belongs to integer. So this value is generated by 4, generated by 12, it may be written as 12z. So which prove our result by fundamental theorem of homomorphism. So this means Z3 which is isomorphic to Z3 which is isomorphic to 4z over 12z. So which prove our result. So in this way we can prove that the Z3 is isomorphic to this values. So here we will use the fundamental theorem of homomorphism. Now next is again very important example question. So if statement is G is finite, G is finite group, G is finite group, then there exists a positive integer k such that x raised to power k equal to identity. Then there exists a positive integer, positive integer. So I take n, it is of more comfortable side, n such that x raised to power n is equal to identity for some x belongs to G. So if it is a of finite group, then it means it has element of finite order. So it has element of finite order. The x raised to power n is equal to this kind. So this is again very important question. So it is GNDU 2011 and 2012. Now this is my statement, this is my question. So G is finite group, so it has some finite element, just some finite order. So I take H which is of this kind, a raised to power r, where r is belongs to integer, r is integer. So if r belongs to z, it is an integer. So we already proved that this is a subgroup. So we already know that it is a subgroup of G. So that is in the previous part. So you easily prove that H is subgroup of group G. So it is in Lagrangian theorem we prove that. So it is a subgroup of group 3. So because it is a generated by A, so also we can say that it is a cyclic subgroup of group G and generator is A, so H is generated by A because it is a cyclic group, so they have the same order. Order of H is equal to order of A, this values. Now by Lagrangian theorem, we know that this is equal if order of A is finite. Now by Lagrangian theorem, we know that order of H divide order of G, so it means order of H is finite. So since order of H is finite, that implies order of A is also finite. Also we can say that H is a part of G and G is finite order. So that can be written as order of A is finite. So if order of A is finite, so in this way, if order of A is finite, so then it means A raised to power n equal to identity. If A raised to power n equal to identity, so we find in this way, right? So we find we find this element A raised to power n equal to identity. Now, so this is very simple result. Now, this value, the question, so how we can find the kernel of a homomorphism? So find statement, find the kernel of homomorphism. Homomorphism. So my first question is A part, which is f from Z to Z3. It is a residue modulo 3 and it is given by f of z, f of x equal to x bar. So how we will find the kernel of this function? So first check the value of what is z. So z is additive group of integer. What is z3? So this is a remainder 0 bar, 1 bar and 2 bar. So this is a modulo 3 element. So when any integer divided by 3, the remainder are only 0, 1 and 2. So this is in 3. If I take here, it is n, so I take in general term. So in that case, this is a Zn, which is a 0 bar, 1 bar, 2 bar, n minus 1 bar and modulo n, right? So in this way, first find the value of Zn. So what is kernel of f? So to find the kernel of f, so I take some element x which belongs to kernel of f. So what is x? X is integer. So I take m ja n. It may be chalo. X belongs to kernel of f. It implies, so since the domain is integer, so x is always part of z. So remember that x is part of z. So it means s of x equal to identity. So what is identity? Identity is 0 bar. So by definition, x bar is equal to 0 bar. And what is this? So this is a x congruent to 0 modulo n. So it implies, so what is x? X is congruent to 0 modulo n, right? So what it means? It means n divide x. What it means? X is multiple of n. Multiple of n means n r, where r belongs to z. What it means? It means x belongs to generated by n. So reverse this process. Reverse this process. So what we get? We get kernel of f is equal to generated by n. So in this way, we can find the kernel of f generated by n, right? So this is a kernel of f of this set. Now, after the second example is, if this is a kernel of f is this homomorphism. Now, after that, if the second example f mapping from G to Z2, right? So Z2, we know the Z2, that is a modulo 2, residue class modulo 2. What is G? So G is a quaternion group. So you read in the first chapter, quaternion groups. So what is the quaternion group? So first see that. So this is of this 2 by 2 matrices G, whose first matrices is identity 1 0 0 1, one element, then iota 0 0 minus iota, and then 0 1 minus 1 0, and then 0 iota iota 0, this values, and minus 1 0 0 minus 1, and then minus iota 0 0 iota, this values, and 0 minus 1 and 1 0 here, so changing this element, and 0 minus 1 1 0 0 minus iota minus iota 0. So what is this element? 1 2 3 4 5 6 7 8. So order is 8. Now this basically group can be written in this way. This can be, E is identity. So this is the identity. So this can be written as, which is equal to identity plus minus E, right? So this is identity. One is plus and second is minus. So plus minus identity plus minus A, two element plus minus A, plus minus B, and plus minus AB. So these are the 8 elements. If these are the 8 element, so EAB, where E is 1 0 0 1 and A is iota 0 0 minus iota, and B is 0 iota iota 0, this values. So these are the element of these values. Also we E, A and B, so this is also generated by either A or B. So this is generated by A and B. So this is the value of this. Now also we can check that some property a raised to power 4, which is identity ab square is equal to a cube and ab is equal to a cube. B square is equal to a square, ab is equal to a cube. So these are some property. Now to find the kernel. So what is the kernel of this f mapping from G to this values Z2? So what is Z2? Z2 is 0 bar and 1 bar. This values modulo 2. This values. So kernel of f here is, so just we prove directly. So kernel of f. So this is a set of all x belongs to G such that f of x equal to 0 bar. This values. So f of x equal to 0 bar, which is identity of Z. So this is only one element, that f of x. So f of x can be written as by definition. So this f of x, we take the mapping of this kind, f of a, which is equal to 0 bar, and f of b, which is equal to 1 bar. So because it is generated by two element a, b, so basically the homomorphism is, here it is two element 0 bar and here it is 1 bar. So if it is E, A, B and third element is AB, so A is going to 0 bar, this values, and because it is generated by these two elements, and B is going to 1 bar. So only one element going to 0 bar. So if one element going to 0 bar, then this set kernel of f consisting only a element. So this is a kernel of f, right? So this kernel of f consisting this element. So this is its image is equal to 0. Now this is the question of this kind, how we can find the kernel of f, kernel of any homomorphism. So in this way we can prove any kind of questions. So next I am taking again very important example. So this is let G, this is a group of all non-zero, complex numbers, right? Non-zero complex number under multiplications, multiplication. So basically it is 2 by 2 matrix. Let G dash, G be a group of all non-zero complex number under multiplication, and G dash, this, it is a group of 2 by 2 matrix. So it is a group of 2 by 2 matrix which is of kind A, B, minus B and A, where not both A and B are 0. So this is 2 by 2 AB belongs to real number, right? So this is a group, right? And where both A and both A and B are 0. So 1 may be 0, not both A and B are 0. So this is a group under multiplication. So we have two group. One is G of all non-zero complex number, that is under multiplication, and second is G dash. So my aim is show that G is isomorphic to G dash, right? So G is a group of all non-zero complex number. It is a non-zero. So its element are A plus iota B, where A is non-zero and A plus iota B is non-zero, and G dash is equal to this values. Now to prove it is a isomorphism, now define a map. So define a map which is equal to F from G to G dash. Now we know the element of G, which is non-zero complex number, and element of G dash. So this is defined by F of A plus iota B, which is equal to this matrix: A real part, B minus B, and A, where for every A plus iota B belongs to G. So this is equation number 1. Also, we know that A plus iota B belongs to G. It implies A plus iota B is non-zero. It implies either A is non-zero or B is non-zero. So it satisfies its condition. So clearly it means our mapping is well defined. Why it is well defined? Because it satisfies the property of both groups. Here A and B both not equal to 0, that is satisfied. Now to prove homomorphism 1 1 and on 2. So first I take two element, let A plus iota B, C plus iota D, it belongs to G. So this value, so first I take the, because they are grouped under multiplication. So A plus iota B and this product C plus iota D, this can be written as simplify AC minus BD plus iota AD plus BC, this value. Now if this product is equal to this, can be written in this way. So what is the F of AB, A plus iota B, C plus iota D, this value. So this value can be written as F, just write AC minus BD plus iota AD plus BC, right? Now, write it in a matrix form. So, write it in a image form. So, it means, so this part is real. So, this part is real and this part is imaginary. So, first I take real part, which is AC minus BD, then imaginary part AD plus BC, and then minus imaginary part minus AD plus BC, and then real part AC minus BD. So just by definition of our matrix. So this is one way, and the second way I take f of A plus iota B into f of C plus iota D. So write it in a different way. So this value is this value AB minus B A, here CD minus DC, this value. So this is a value of this. Now multiply these values. So first part, this value by multiplication. So this is AC minus BD, and second is AD plus BC, and here minus BC plus AD, and next is minus BD plus AC. So AC minus BD, this values. So clearly f of A plus iota B into C plus iota D, this value is equal to f of A plus iota B f of C plus iota D. So it satisfies the property of homomorphism. So it implies this mapping is a homomorphism. Homomorphism. This mapping is a homomorphism. Now to prove isomorphism, I need to prove 1-1 as well as onto. So 1-1 f of A plus iota B, which is equal to f of C plus iota D, it implies AB minus B A, this is C D minus D C. Since both matrices are equal, it implies A equal to C and B equal to D, this value. It implies A plus iota B, which is equal to C plus iota D. It implies F is 1-1. So clearly it is a 1-1, right? So this prove our 1-1 property. Now next is onto. So clearly, since AB, this to prove the onto. So let I take matrix AB minus b a, this value, it belongs to g dash. So this is from g dash. Now, not both a and b are 0. So since not both a and b are 0, it implies a plus iota b not equal to 0 also belongs to G. Also belongs to G, and also its image a plus iota b, which is equal to a b minus b a. So it implies this map F is onto. So that is my result. This map is onto. Now F is 1 1 onto and homomorphism. So this G, which is isomorphic to G dash. So that prove our result. So in this way we can prove it. This is a isomorphism. Now again, to prove the next result, I just give the idea of that result. The statement is prove that any cyclic group any cyclic group of order n, this is any cyclic group of order n, is isomorphic to group of nth root of unity, nth root of unity under multiplication. So prove it, these are isomorphic. So how we will prove it, right? So first understand the nth root of unity and then the cyclic group of order n. So if I take G dash, which is a cyclic group of order n, so where order of A is equal to n. So I just give an idea. So do it yourself. So it means it has element E, A square, A raised to power n minus 1. So it is a cyclic group of order n. And G is nth root of unity. It is a nth root of unity. So what is the nth root of unity? So we know that x raised to power n, nth root of unity is x, which is 1 raised to power n. This values. So this is a cis pi plus 2k pi, cis 0 plus 2k pi raised to power n, raised to power 1 by n, nth root of unity raised to power 1 by n. So this is cis 2k pi raised to power n 1 by n, where k is running from 0, 1, 2, so on up to n minus 1. This is can be written as e raised to power iota pi. This also written as. Now this is basically, so just understand first this values. So x is equal to, says 2k pi by n, this values, where k is running from 0, 1, 2, so on up to n minus 1. If you write this is e raised to power iota, e raised to power, just cis, you can write either in cis or e raised to power. So e raised to power now iota. So this is e raised to power iota 2k pi by n. We also write it in this way, and this can be written as e 2 pi iota by n and raised to power k ja r. So this is k. So it means if I write for simplification as alpha, so I write in simplification, so let alpha is equal to e raised to power 2 pi iota by n, ja cis of 2 pi iota by n. It may be any number. So it means this value g, which is equal to this values, k is 0 to 1 by n. So this is 1 alpha, alpha square, so on up to alpha raised to power n minus 1. So this is the element of g. This is the element of g, and element of g dash, element of g dash are e, then a, and so on up to a raised to power n minus 1, this value. So this is element of g, this is element of g dash. Now define a map of this. 1 goes to e, alpha goes to a. So 1 goes to e, alpha goes to a, alpha square goes to a square, and alpha raised to power n minus 1 goes to a raised to power n minus 1. So this map will be homomorphism 1, 1 and on to. So how we will prove it? So define a map in this way. So define a map. So define a map f from g to g dash. So this is defined by f of alpha raised to power r, which is equal to a raised to power r for every r is running from 0, 1, 2, so on up to n minus 1. Then prove that this mapping is homomorphism 1, 1 as well as onto. So this mapping is homomorphism 1, 1 as well as onto. If this value is 1, 1 and onto, then it implies G will be isomorphic to G dash. So in this way, do it yourself. So this is idea regarding this question. So this is a G is isomorphic to G dash.